Before we will start our presentation, I would like to first introduce myself. My name is Grzegorz Wypych. I'm living in Poland. I'm currently working around 15 years in IT. In the past, I had different positions like network engineer, architect, also developer for both backend and frontend and different applications. Then I moved to the security field. I'm one of the author of the Raiden that will be presented. Today I also had pleasure to present on different conferences in USA, like Hardware I/O, or in Europe and in Poland. And now I can present on the Black Hat, which is uh, also pleasure and nice nomination. Other than that, I mostly focused on the software and hardware side when doing security tests. I hold a master degree, and I don't have currently any certifications, but in the past I had also CCIE from Cisco when I was worked as network engineer. For now, my current position is senior security consultant for IBM X-Force Red. Thank you.
And I'm Laurie. I also work for IBM X-Force Red as the lead hardware hacker, and I'm an associate partner there. I've been in this industry for over 30 years, and I started in the defensive side of the house, the blue team, and more recently have moved over to the red team doing offensive security, specializing in hardware and embedded systems. So before we begin, we should talk a bit about what is Raiden and actually what is glitching. So Raiden is a glitching tool, and glitching is the process of introducing a fault, but a very precisely controlled fault. So normally it's done to the clock or the power lines on a chip, but it can be induced via EMP or light or heat or anything that causes the device to malfunction. But power and clock are the most easy to control very precisely, so that's where you normally see it. So basically what it's doing, as you can see on this oscilloscope trace here, you're introducing very, very short glitches or drops in power at a very precisely controlled moment. So if you do it precisely enough, you can actually corrupt a single instruction. So for example, if a value is being loaded from memory, from say flash RAM into memory on the chip, if you glitch at just the right moment, you potentially can corrupt that value. So if that value is being used to check security decision like a password or a yes/no state, then if you corrupt it at just the right moment, you can potentially override that decision and change the outcome. If you glitch too hard or at the wrong time, essentially you can just crash the device altogether. So what we need is a tool that's very precise and easy to control. So the plan when we started looking at Raiden, we looked at tools that were available on the market, and some of them were expensive or overcomplicated. And so we wanted to just create something that did everything we needed to do, but was very low cost. And I'm a great believer in open source, so I wanted to open source it. Happily, we've been allowed to do that from our employer, so we will be publishing the code after this. So yeah, we wanted very low cost, open source, and so to do that, we settled on a very simple FPGA design But that also means it's very easy, because we're using standard Verilog, it's very easy to port that onto other hardware. So if you need a faster glitcher or a more powerful processor or whatever, you can just switch to a different platform and it should port pretty easily. We also wanted it to be independent of the final delivery mechanism. So the glitcher is purely for timing purposes. It's not delivering the actual fault into the device. So it controls either a power amp or a power switch or an EMFI injector or whatever. So its only job is to do the logic of when you want to glitch, how often you want to glitch, and the width of the pulse and so on. So for the hardware, we settled on this guy, the Xilinx Arctic 7, known as the RT. Very low cost, very powerful board, and very easy to program and to hook up. It's got loads of, as you can see, it's got a whole bunch of GPIO ports, so very easy to connect. And Grzegorz is going to talk more about the actual detail of what goes on inside.
Okay, let's look inside Raiden. So here on the screen we can see Vivado Studio. This is kind of the IDE that we use to create Raiden and Verilog code, because the Verilog is the core of the Raiden. The first file that I would like to show you is constraints file. This file defines different signals that are used by a Verilog. So we can treat it as like variable name or something for standard programming languages, but this is just a signal name that we use in our code. Some of the signals, as we see, have additional configuration for a pull-up, which is required to handle correctly the signals. The top module is a module that has instances of different modules, and here we have definition of our output and input signals based on the constraint file. We have some wires that wire our signals with the registers. Here we have like command module, which is responsible to handle all the commands sent over UART to the Raiden, and it's getting some inputs and giving some outputs that are used by different modules, like the most one imported, which is a glitch module here. So the glitch is instance of the glitch module, and it gets like delay, width, count, the gap, v start max, and other register values that are handled inside. And based on the values that we are want to send and use in Raiden, module is responding on that in the inner state machine. This is just a PWM instances, just for LED indication and some kind of debugging what's going on. So top module, as I mentioned, have instances of the modules, but if we look on specific modules like command, we can see that it also has some other instances from the receive and transmit modules. These are created by chipfile guys and modified by us for our needs. So we didn't like create a wheel from the beginning again. and invented the wheel, of course. So the command module role is to get Python sent commands, which are represented by numbers, and based on the numbers, we are starting proper action in the state machine. Some commands also get additional data to be processed, like for example width or delay. You need to specify how much delay or what should be the glitch width or glitch count and so on, in order to make your glitching attack. And command module has a big state machine that is actually just handling all the commands. The glitch module itself, it's more complicated because it has some signals that needs to meet specific condition in order to be set, and we don't have enough time to discuss everything what's in the glitch module. But from the top view, this is how the Raiden was created. We have command module, glitch module, and actually these are the most important ones that are our core. And that's all about inner side of the Raiden. Thank you. Okay, so let's look on the front-end side of the Raiden. So this is our Python API. This is the core module, which is not long. I mean, our goal was to create very simple Python code available for everyone to easy understand and use Raiden. So here we have a class Raiden with an init function, which actually just creates an UART connection, the serial connection. Here we just specify, when we are creating instance of this class, specify serial port we want to connect. If you want to have some debug output to track what's going on, and the ticks define if you want to use clock ticks to set some values, or we want to use that in seconds. Here we have a dictionary with all available commands, and earlier I presented numbers that represent commands, and this is actually a front end that has exactly the same information. So the value is just a number that we are sending, and it triggers the proper command handling on the backend of the Raiden. Here we have a function to send Raiden commands. Some of the commands are just an ASCII that we want to receive, and we have 1 byte command handling and 4 byte command handling. These are the key values from a dictionary that use a single byte command. So we are just packing them as a single byte and send them over the wire to Raiden. And here we have 4 byte commands handling, where we are sending 4 bytes over wire, and these are specific commands. What else? We have also possibility for some commands to set a value, like glitch delay or count or vstart or max or whatever. If they are yeah, and this is the arm. So if you want to actually arm our Raiden, to be ready for glitching. Possibility to set target power on off. This is just kind of the flag status handling and it's checking our flags. And actually, it's all. The last one is just a build time when we want to receive the latest information about the code and when it were compiled. Okay. Here we have a bunch of examples for different applications we use Raiden for. Here are interesting one with the USB, and this actually use the file whisperer. Here I have it. So it's new hardware USB trigger, and it actually works perfectly with a Raiden. And enabling the Raiden itself very simple. We just set params. First we like arming to 0, which means we disarm actually Raiden, reset all the parameters, states and everything from FPGA. Then we are sending whatever commands we want, arm it. We can use it to power on, power off, and this is just file whisperer code, and we just wait in the loop until Raiden is not finished his cycle. We're just passing and waiting until the trigger in actually trigger Raiden to set a glitching based on this trigger condition set by the file whisperer. We also use it standalone. Adam Major will present in his demo, and yeah, that's all about Raiden frontend. Now let's talk about Raiden pinout. So if we look on the Raiden board, we decide to utilize basically input and output connections to external shield like Arduino, because they are easy accessible and they have also protected resistors, so it's better to utilize this I/O. First, let's talk about external connections. This is where we can get a trigger in to the Raiden and glitch based on the signal received on IO29. Other IOs we see that like reset out or invert glitch, they are used for other applications that we will also talk about later. But the most important is trigger in this case. Here we have connection with internal trigger. We call it internal trigger, but this is actually the reset out signal sent and generate from the Raiden to the target board. Reset signal actually mostly. So in this connection, what is required is to connect 3.3 volt output pin available on the Raiden to the trigger in directly. So we are creating here like a bridge together, and the reset out signal needs to be connected to the reset of the target device. This will allow us to create our own internal reset out, and based on that we can make an actions to perform glitching. So if we look on the Raiden applications, the first one is connection to the MAX 4619 CPE. It's very common switch used in many other solutions like cheap fair guys project. This is our glitching frontend. and in order for it to work, what is required is our proper connections. So we need two power supplies, or one power supply with a lot of available signals, but we utilize here two power supplies in this setup, and one power supply is providing target core VDD, and the second one is used for the glitch signal that we can handle and the amplitude of the signal. So whenever we will drop or raise up voltage on power supply 1, this is how it should be affected on the oscilloscope and also on the glitch signal finally. What also is required here is a connection of the out signal, which is basically our glitch out signal is on IO15, on the pin 15 actually, on the max, and it's when we are connecting it somewhere to the core voltage of the glitched device. The glitch out signal IO41 is connected to pin 10, and IO29 trigger in is connected to the trigger out signal of the target board. Other connections that we tested and support is connection to the EMFI device, like UI chip shouter. And in order to utilize it, we need to use advanced breakout board and of course have a chip shouter available. But I tested this signal on this setup on the one of the projects, and it worked perfectly, giving nice results. So in this case, what is required, we first need to somehow power on the board. We can do it from a Raiden, from the 3.3 volt outage signal available, or from some other external power supply. We need to connect IO38. It's important, 38, which is inverting our glitch, which is required actually for the chip shouter to handle it correctly. And we are connecting it to the hardware trigger in. We are connecting to the HS2 in, which is basically a clock in on the advanced breakout board. And we need to open this pin on the switch available on the breakout board. I will show that in a minute on the next slide. And from available out port, which is we connected to the trigger in hardware trigger in on the new chip shouter. In this setup, we are not utilizing like a CPU possibility of the new AE. Instead, using the code on the CPU, we're just using a chip shouter as pure EMFI device, right, with EMFI probe. This is basically actually our probe, and internally the hardware trigger in is connected directly to the out probe of the EMFI. And this is a breakout board. Here we see the yellow cable is connecting IO38 to HS2 on chip whisperer side, let's say, of the breakout board. And here on the switch we are opening HS2 to provide connection from here over the switch to this connection out, which is connecting to the chip shouter. And yeah, that's all about connections.
One of the things you need to be able to do is actually see if your glitch is having an effect. So one thing you can do is create code that runs on a chip and play with it before you actually attack a target. So this is a little sort of mini application that I wrote that runs on the LPC 11U24. And it gives you a little menu, and you can do stuff like set the code protection level, dump out the boot ROM, and stuff like that. A few useful little things. But the main purpose is this glitch test. So basically what the glitch test does is it gives you a way of checking if your glitch is actually having an effect. So if I go into glitch test mode, what it's doing is it's reading the CRP value from Flash, which at the moment is not set, it's all Fs. But for the purpose of testing, you really don't care what you're changing it from or to, you're just checking that you can change it. So if I read anything other than FFFF from the Flash, then I've successfully glitched. So when you're actually running the test, what it does is every time you hit a G, every time you send a G over the serial, it will bring a GPIO line high, which you can use to synchronize your glitcher, to actually trigger your glitcher. It'll then do the comparison, and then it will bring it low again. So you can write a script that basically does that, sends a G, glitches at an offset from when that line goes high, and checks the response to see if you get a match or a mismatch. So if I hit G, I'll just get dots because it's always going to match because I'm not currently glitching. But if we automate that process, so I've got a script here which is just going to do that in a loop, so with a bunch of different settings, so different delays, number of ticks from when the line goes high, different number of pulses in the glitch, and different widths of pulse. Just going to try a few things until it gets a positive response from the glitch test. If I come out of here and actually run that, what we should see on the scope script, what we should see on the scope is you see the pulses changing, number of pulses that we're sending. So as we send each glitch, we can see that we're actually having an effect, and at some point we get success. So at a delay of 10 with a width of 3 and a count of 6 pulses, we successfully corrupted that memory, and the comparison failed. So we successfully glitched our chip.
So right in the battle, I would like to show you one of the interesting findings this year. It was part of the research we've done with Major, and it was about USB stack security. Last year, UI company released a great hardware trigger called Phi Whisperer, and it it put our attention on it, and we started figure out how we can use it and utilize it together with Raiden um, to get something interesting research. So we started with selecting a target, and our choice go for STM32, the WB55. It's popular Nucleo STM board. It's the newest one that supports also Bluetooth, ZigBee, and stuff like that. And we started searching information what USB stack it's using, and we found that entire line of STM32 microcontrollers use the same USB stack. So if there will be any issue there, this will probably affect more than just one microcontroller. Here we of course see a screen showing that we connected device to PC, and we also uploaded the code to microcontroller to simulate, for example, a joystick or whatever USB device we wanted. So before we'll go to the details of our finding, we want to first show some information about USB descriptors, because this is the very important point of the research. So USB descriptors are just small messages sent over a USB bus, and they are used for different things. One of them is just sending control messages, and other also can be used to send some data. And the most important field in the USB descriptor is WLAN field. It has 16 bits, which mean potentially we should be able to send up to 65,535 bytes, but mostly we don't need this amount of data when we are just sending when the WLAN field is calculated of the USB descriptor message. So we started looking for a code for any queries or points where this length is checked or not checked, and how it's used by a code. And we found very interesting point. It was under USB heat descriptor class, and also for the same actually was for the other DFU class. And if you look on the line 499, trying to zoom that a little bit, we can see a min function, and also on the line 505, which actually it's trying to get the minimum value between the VLAN that is read from a packet and some configured static variable defined in the code. So where is the problem? Well, if we look on the code itself, it doesn't look bad, right? Because we have some minim function that is doing this check. But what if we will be able to corrupt this function? We have a code, so nothing stops us from, for example, selecting one of the I/O ports on the target board, use it to set a trigger just a little bit after or before the one or the second function, and try to send a glitch that will finally corrupt this function, and maybe the size we will send and craft in our USB message will overwrite whatever was before. So let's look on the research setup. So here we see a bunch of the devices, starting from the left top corner. We can see Raspberry Pi. It could be also PC. It's just used to connect File Whisperer and other devices like our Raiden chip shouter together, right? To give it the power, UART access, and so on. So in the earlier slides, I presented the option how we can connect EMFI device, and this is one of the setups. So we know already how to connect over breakout board the chip shouter to the Raiden, and um, and additionally we added file whisperer for USB triggering, because we want to trigger on specific USB messages. Before we were actually glitch in the point where we want under the min function. So let's look how it worked. I mean, I recorded a video because from glitching is unpredictable. I mean, it could take 10 minutes, it could take 1 hour, it could take days. So I pre-recorded and actually just cut out the most important part of the glitching process because otherwise the video could be too long. So let's go for it. I will now run it. And here we can see at the beginning an exception, control transfer, error, no such device, and it was disconnected. These are just resets sent from file whisperer to the target board because each time the glitch is not success, we want to restart device and start from scratch. So in the here on the bottom we can see delay, some delay set, width and repeat, and this delay will change during test process. Now it's like 3402, and we go forward until we finally hit our IO under the min function that we configured, and here we get like 65,000 bytes of the data. So if we will just do a quick hex dump on this of the information we just received, we can see a bunch of good bytes, which means we corrupted the min function, and actually we received more data than we expected over USB. And this data could be anything. It could be some information about secret key stored. The severity of the problem depends on what was after the USB descriptors structures. So if there is some memory shard there and there will be sensitive information, it will be spit out over USB, and that's definitely a vulnerability that we can use. Okay, so let's now look on the code. I mean, because I mentioned earlier that integration between Raiden and other third-party devices is easy, and I want to prove it on Python, on simple Python script that actually executed what we were able to see on the pre-recorded video. So let me quickly go to the terminal and let's look on the code. So here we have a function. I utilized here file whisperer possibility to make restarts, I mean power on, power off device. Here we have a Raiden, a configuration for a UART. Here we have chip shouter UART connectivity, and also we have configuration for the file whisperer. So what is most important in this setup is that everything needs to be in the correct order. So we first reset all the state of the Raiden, put required parameters we want to use during glitching. There is some information that should be printed as a debug when the glitch is going. It was not on the video because I mean this addition to the code was written later than the video was recorded. Um, Here we have setup for the file whisperer, and the most important part is a pattern. So these are just the bytes on the USB bus. If they will be seen, it will be triggered. The file whisperer will be triggered IO4 high, which will also trigger our Raiden, and of course it will be for this will be forwarded to the EMFI, which will inject electromagnetic field changes. So here we are arming file whisperer, and this is the packet we are sending. So we are sending this USB message, and we are requesting this length. So normally this will not be accepted, but during a glitching, when the glitch will success, we were able to see actually that we can get this amount of data that we request over USB back to us. And here we have infinite loop waiting until Raiden will not finish its cycle. If it's not success, then we pass and start over. So we can see that it's very easy to actually use with Python 3 devices: File Whisperer, Chip Shouter, and the Raiden, and they perfectly synchronize to do their job. Okay, so that's about this vulnerability. We of course have CVE4, and after we release Raiden code, we also release these examples, and they will be publicly available. Thank you.